research designs. So what kind of research designs do we have that are less straightforward and that are less easy to understand? We will take a look at incomplete designs, mixed designs, and also small n designs during the remaining 20 minutes or so. Just for you to have an idea of what those designs are. Of course, maybe you will never need them in your life, but at least you need to have an idea of what these are. When you read other people's papers, this will help you to understand things a little bit better. First of all, what are incomplete research designs? So far, we have introduced the notion of a factorial experiment or factorial design, when we have imagined that we have two independent variables, each of them with two levels. As a result, you have 2 by 2, 4 experimental conditions. In a full factorial design, the number of experimental conditions, which are unique combinations of the levels of your independent variables, grows in geometric progression with the growth of the number of your independent variables and of their levels. So imagine that you have 3 independent variables, each of them with 2 levels. The number of groups is 2 by 2 by 2 is 8, which is a bit much, but maybe it's still feasible. But if each of these variables has 3 levels, the number of groups is 3 by 3 by 3, 27. Oh my gosh, it's a nightmare to conduct such an experiment. It will take you ages and ages. Your expenses and the time needed to conduct this grow exponentially in geometric progression. So we need some kind of tricky strategy. We need some cunning plan to reduce the number of groups. And this cunning plan is called incomplete designs. The classical example of an incomplete design is a Latin square design. Imagine that I have 3 independent variables, each of them with 2 levels. But I say I only want to use 4 groups. So the best thing I can do is I can distribute the levels of my third independent variable across the levels of my first 2 independent variables. So that for each level of my IV1, for example, treatment, I have both levels of IV3, A and B. And the same for control level of IV1, I have levels of IV3, B and A. And for the second IV, which might be present or absent, I also have both IV3A, IV3B, and IV3B, IV3A. As a result, why is it called Latin square? If you remember from school, a Latin square is a table where the same number appears only once in each column and only once in each row. And this is exactly the case here. So for IV3, we have A and B, and in each row and in each column of this table, A appears only once and B appears only once. But they are distributed equally across columns and rows. So in each column and in each row, the number of times A and B appear is exactly equal. This is a perfectly balanced Latin square design. What are the advantages? Instead of 8 groups, I only have 4 groups. What are disadvantages? I get less data, I have less statistical power, and also I am not able to estimate the interaction effects between the 3 variables anymore. Because I don't have 1/2 of my data. I don't know. Maybe if IV1 is treatment and IV2 is present, and if IV3 was B, something strange would be happening. Maybe there would be some difference. So I am not able to estimate this 3-way interaction. But 2-way interactions I can estimate more or less well. And this is often used in business, for example, where expenses are very important to conduct an experiment. let's imagine, for example, that you are the owner of a taxi company and you are interested whether the fuel consumption depends on car brand, on the proficiency of your driver, and on the type of route that this driver is taking. So in your taxi company, imagine that you have Porsche, BMW, and Mercedes. So it's a good taxi company. Congratulations. And you have 3 types of drivers with 3 different amounts of experience. Maybe novice drivers who just started working at your company. Maybe experienced drivers who worked, let's say, for half a year on average. And professional drivers who worked for 1 year or more. So you form these 3 groups of drivers, you have 3 types of cars, and you have 3 types of routes. Some orders involve only city center, some orders involve more remote areas, and some orders involve driving to the airport on the highway. So altogether you have 3 independent variables, and you have 27 unique conditions. So if you want to conduct such an experiment, for each of the 27 conditions, you need to have many measurements. So you need to have 27 cars driving for many days on different routes, etc. Obviously, in practice, this is not very feasible. So I can say I want to cut down on my expenses by a factor of 3. I want to spend 3 times less time and 3 times less money conducting this study. So I will distribute the drivers across car brands and across road types in a Latin square approach, just like in this table, so that my novice driver drives once Porsche, once BMW, and once Mercedes, and the same goes for pro and experienced. And my novice driver goes once in the center, once in the side streets, and once in the highway. And the same goes for the other 2 drivers. So as a result, I only have 9 unique experimental conditions summarized in the cells of this table. So my novice only drives Porsche in the city center, only drives Mercedes in the highway, etc. And of course, for each of these conditions, I will need still to collect many measurements to get sufficient precision. But still, it cuts down on my expenses. But the drawback, I cannot really test some interaction effects. Maybe if novice drives a Mercedes in the city center, he or she is much more efficient than if they drive this Mercedes on the highway, and so on. So these interactions, I just don't have data. But if I don't need these interactions, I don't care about them. I just want to know which car, which driver, and which route influences fuel consumption, then it's a well-designed experiment. I get enough data to make my business decisions. And in science, we also sometimes use Latin square designs, especially in cognitive science, where you have many independent variables with many conditions, and it's very hard to actually conduct a full design. You will have your participants with you for ages. But of course, Latin square design is not the only type of incomplete designs. There are many, many, many possible incomplete designs. Let's take, for example, this fractional factorial design. When imagine that you have a factory, and at this factory you have a special machine making some kind of product, and this machine has 18 handles. And these 18 handles can all be either switched high or switched low. So you have 18 handles, and the number of unique combinations of the settings on these handles is 2 by the factor of 18, 2 by the power of 18 is 2048 unique combinations. And if you want to find out which combination is optimal for production, oh my gosh, you will have to spoil 2000 or more batches of material to produce your product. Obviously, it's not a good idea. But we can say, okay, let's create a more or less randomized combination of these settings so that in about half the situations, each handle is switched high and low. And as a result, we can spoil only 16 batches of material to get a good understanding of how each handle individually affects the quality of my products. Of course, I may not quite be confident about interactions, because here for each interaction between each pair of handles, I only have 4 observations, which might not be enough. But when I generate this design using statistical software, even SPSS can do it, I tell my software which effects I'm interested in, how many measurements do I need of each combination, and it generates for me this design. So I can cut down on my expenses. If I have 11 handles, it does not mean I need to test all possible combinations. Maybe just 16 trials instead of 2048 will be sufficient. So these are incomplete designs that allow us to cut down on our expenses. Another tricky type of designs are repeated measures designs. What are repeated measures? It's a situation when all my variables, all my independent variables are within group. Obviously, I can say I have one group and I do one thing, another thing, and third thing, and I measure every time. But this is not an experiment because I don't control for position and sequence effects. If I want to make sure that I have measurements for each experimental condition, for example, juice, independent of the sequence in which the juice was tasted, I need to control for position effects using, for example, counterbalancing. So the number of possible sequences of 3 interventions is 6. It's basically 3 factorial. It gives me 6 possible sequences. But of course, if I have more than 3 levels, if I have 4 factorial, it will be 24 possible sequences, etc. It might not be feasible anymore. So I can also use a Latin square to reduce the number of possible sequences. And for repeated measures, Latin square helps me to reduce the number of my groups. And finally, the third type of research designs is the situation when I have some between group designs and some within group designs. This is called mixed designs. Unfortunately, in the literature, there is also a little bit of confusion because let's take, for example, the first design, which is called longitudinal design. In one group, we have some measurements, then there is some intervention, and then again some measurements. In another group, the same thing, but there is no intervention or a placebo intervention. Goodwin would not call it a mixed design even, because there is no within subject independent variable. But Shedish and Cook, they say, actually time is also an independent variable, even though we don't manipulate it, but we can say that the difference between pretest and post-test is also potentially an independent variable, the time that changes something in the variance of my dV. So here we can treat time as another independent variable, and this will be a mixed design. Another example of such a design is called crossover design. If you have 2 interventions, for example, 2 juices, and you might have pretest intervention 1 measurement, intervention 2 measurement, and another group receives these 2 interventions in the reverse order. So when you analyze statistically the result of this experiment, you have 3 effects again. The main effect of time, the difference between, let's say, pretest and post-test. The main effect of intervention, the difference between intervention A and intervention B. And 3, the main effect of order. So basically the difference between group A and group B. And obviously there will also be some interactions between those potential. So mixed designs like this are fairly common in social sciences. Whenever you have 2 groups and you conduct some experiment with those 2 groups, and one of your independent variables is time because you have pretest measurement and post-test measurement, you normally use mixed analysis of variance. And the hypothesis that you are interested in is whether the change from pretest to post-test is the same or different in these 2 groups. If the change is different, maybe your intervention had some effect. But if the change is the same, maybe it's due to some background effects or maturation, etc. So to take a look at an example of such a study, we can use an example of the study that we conducted with my colleague, Ilona Bonival, when we tested the effects of an intervention for schools called Personal Wellbeing Lessons. Ilona and her colleague Lucy developed a teaching course targeting secondary school students, which aimed to help them develop skills for a psychologically positive life, to interpret things in more optimistic ways, to become more resilient, to manage their emotions. So there is a sequence of something like 24 lessons that take place over a school year, and each lesson is devoted to a specific psychological topic, and students interact and they practice their skills, etc. So we wanted to test whether this intervention would improve the well-being of students. So we had 2 schools from the same federation of schools, one experimental school and one control school. But of course, with 2 different schools, we could not randomly assign our students. So it was not a completely randomized design. It was, strictly speaking, a quasi-experiment because we could not guarantee that our groups were equivalent. But there was a placebo intervention. So in one school, the students were receiving these personal well-being lessons over the course of the school year. And in another school, control school, they received the old personal, social, and health education course, which also has some psychology in it, but it's kind of much more boring and standard. So we were looking for the effects of whether the effect of our intervention on the change from pretest to post-test would be different compared to the old intervention. And we had data measured in September and in June. There were a lot of challenges because teachers forgot to ask some students to sign their questionnaires, and we lost a lot of data just because of this. We could not match the data in September and in June for some people. So we were left with 96 people in the intervention group and 68 people in the control group, which was still not too bad. And we measured satisfaction with life by domains, satisfaction with self, friends, school, etc., satisfaction with life in general, and we measured positive affect and negative affect experienced over the past 2 weeks. So when we looked at those results, I have summarized them here in the table for you. This table comes from our paper. This is how you would normally present your results in such a design. So there are measurements for pretest, for the intervention group and for the control group, and there are measurements for post-test for the intervention and for the control group. And for each of these measurements, you have a mean and a standard deviation, 2 statistics that are sufficient to describe a distribution if it's normal. So satisfaction with self, for example, in the intervention group at pretest was 4.81 and 4.79 at the post-test. There was no statistically significant change. But for the control group, there was a statistically significant change. Satisfaction with self declined from pretest to post-test. So this way we compared pretest and post-test in each group, and we found that in the intervention group, 2 variables declined, 2 did not. In the control group, 4 variables declined. So, wow, what can we do? What can we conclude based on those findings? The students all became less satisfied at the end of the school year. And when we looked at this data, we did a little bit of facepalm. Oh my gosh, everything gets worse by the end of the school year. Is our intervention even beneficial? And that's the problem that people often face in these research designs. Because you can perform what we call simple effects analysis when you just compare in pairs. You compare, for example, pretest to post-test in the intervention group, pretest to post-test in the control group, or you compare 2 groups before and 2 groups after. But if all you can do are these simple effects comparisons, you are not able to test your most important hypothesis. Is the change from pretest to post-test the same or not the same in 2 groups? And this is why you need to use a mixed ANOVA, and you need to test for this interaction effect, which is exactly what we did in this study. So here we have a table of results of ANOVA, the F statistic, which is after Fisher. It's called F statistic. And the eta squared, the effect size, and statistical significance marked with asterisks. And here we have main effects of time, main effect of group. But we are not really interested in those main effects. Do we really need to know whether at the beginning and at the end students were different regardless of what group they are from? Maybe it's some kind of background effect, but we are not really interested in it. And the same goes for group. Are we interested in knowing that in experimental group students were higher or lower regardless of the time of measurement? Also, we don't really care about this one. What we care about is this interaction between time and group, which tells us that the change from pretest to posttest was not the same in two groups. And we discovered some significant effects. And here you can see that, for example, for satisfaction with self, in the control group, it dropped. In the intervention group, it almost did not change. Or satisfaction with friends. In the control group, it dropped a lot. In the intervention group, it dropped a little. And this difference is statistically significant. The only variable on which we observed the effect in the opposite direction was satisfaction with school. In the control group, it dropped a little. In the intervention group, it dropped a lot. How can we make sense of all of these findings? Basically, we observed that both groups showed some decline in their well-being scores from pretest to posttest. And when we looked at the literature, we found out that this was completely common. No matter what it is you measure, if you measure in September and in June, students and teachers are all burned out. They start hating their school, hating studies, and all they can dream of is vacation. This is well-known school burnout. So it's predictable to see that in both groups, scores have dropped. But the fact that they have dropped less in the intervention group already suggests that the intervention was effective. And the only variable where it had a paradoxical effect was satisfaction with school. And when we thought, why? We thought, well, maybe before this intervention, in case of any problems, children were likely to blame themselves. But given this intervention, which included some elements of optimism, maybe they learned that you need to be more differentiated. And they started also to see the causes of their problems in their school environment. As a result, satisfaction with school has decreased a little bit more in the intervention group. But overall, we concluded that this intervention was good and it produced a buffering effect against the effects of school burnout and school transition. So these are the mixed effects. A couple of other tricky things that you might or might not ever encounter in your research life. Our independent variables might be of different types. Some of them are called fixed factors, and some of them are called random factors. If you are testing the effect of intervention versus control, you are only interested in the effects of at these two conditions. But if your independent variable is, for example, the loudness of music, you can choose certain levels of loudness out of a whole range. Or if your independent variable is person, and you have many measurements produced by each person. These are random factors, because the levels of these variables represent a sample from a large possible range of levels. And statistically, you can use different models. You can use model for fixed factors, and then you can only generalize to those levels that you used in your experiment. Or you can apply a much more complex model for random factors, and then you can generalize a bit more. But these random factor models, they are a bit tricky to compute. And another thing that is a little bit tricky is nested factors. When, for example, you are interested in the effects of individual teachers on students' academic performance, but those teachers are nested within schools. So you have a school with many teachers, and you have another school also with many teachers. So then all teachers from the same school, they have something in common, because maybe they have the same headmaster. One headmaster is nice, another headmaster is awful, and this impacts teachers' performance, and this probably impacts the resulting students' exam scores. So if you have this kind of nested design, you will need to use a multi-level model. Unfortunately, if you ignore this hierarchical structure of your data, you might obtain biased estimates of your experimental effects. But we will discuss a little bit about multi-level models later on in our course, so you'll have an idea of what they are. And the final tricky type of research that sometimes we are interested in are small n designs, or designs for small samples. Some people, when we learn psychology, we learn about all those wonderful experiments. Here you can see John Watson and Rosalind Rayner torturing little Albert. And maybe you know that John Watson had to leave academia because of his affair with Rosalind Rayner. So maybe it was the karmic revenge for this poor little Albert's suffering. And here you can see also Lev Vygotsky conducting his psychological experiments with his daughter Gita, and his wife Rozanoyevna is his assistant. So basically most of experiments by Vygotsky were conducted with 2-3 children, and they were his own children. And the same with little Albert, just one child and a whole experimental, a large-scale conclusion. And some people, when we read those stories from the history of science, we ask the question, if John Watson and Vygotsky could use such small samples, why can't we? But if you naively say, I will have 5 participants in my study, because Zimbardo in his Stanford prison experiment, he had something like 10. So if Zimbardo could, why can't I? You miss the important difference between different types of studies. In a normal experiment, which we can call a large sample design, we have a large number of individuals, and we are interested in the differences across the levels of our independent variable, and we perform statistical analysis to evaluate these differences. This allows us to generalize things. In studies like the studies of John Watson or Lev Vygotsky or Ivan Pavlov, there were always a small number of subjects, and there were all the levels of the independent variable administered, but there were many measures, and the analysis was mainly visual. It was mainly qualitative. So why do we trust these findings of John Watson or Ivan Pavlov or Lev Vygotsky? It is due to replication. It is not due to statistical analysis, because there was not enough data, but it is due to the fact that Ivan Pavlov's findings were replicated in many labs with many different dogs, and even if he discovered it with one dog, he replicated it with other dogs, and other people also replicated. So it's thanks to this replication that validity of these findings is established. And we can think of these small n designs as a special kind of study. Sometimes it's called qualitative experiment, because it's not even so much a nomothetic quantitative approach. It's mostly an ideographic approach. When we are interested in individual variability, and we try to observe, we try to record whatever happens, and we try to just see what happens. Stanford prison experiment was conducted also this way. But we cannot generalize. We cannot be confident that the same thing will occur in a different sample. However, if you just want to demonstrate that something, some effect takes place, as Zimbardo wanted to demonstrate the power of situation over people, and to describe the experiences, to describe the potential effects, and to use this as a source of qualitative evidence to inform future, more quantitative studies, this approach is good. So it's a kind of a qualitative approach to experimentation, and it's good for some exploratory studies. So we have taken a look at different tricky models of experiments, and today we started with a discussion of the principles of causality and how we can ensure these principles of causality in experiment. Then we took a look at different variables and what role they play in experimentation. And then we tried to take a look at different experimental designs, between group designs, within group designs, and more complex designs with separate independent variable, as well as special cases like incomplete designs and Latin squares. Obviously, it's a lot of stuff. I don't expect you to grasp this lot of stuff in one go, and based on your performance at seminars and tests, we'll see whether you managed or not. But I totally invite you to read some good literature. If this is the first time you're encountering psychology and you're encountering this whole bunch of material about experimentation, I would recommend you to start with the textbook by C.J. Goodwin, which is available in English and in Russian for Russian speakers, where he provides a more gentle introduction to experimentation. If you are a more mature sea wolf, if you are already a rat who knows a lot of experiments, I recommend you this good book by Shedish, Cook and Campbell. Or sorry, Shedish, Cook and Thomas. It's a mistake on my slide. Cook is the same Cook who collaborated with Don Campbell in the 1960s, and they basically developed a little bit Don Campbell's paradigm, but it's basically the same classical textbook of Campbell and Stanley brought up to a new level. If you want to see a more classical version, there is also Campbell and Stanley, where they discuss those designs. In Shedish and Cook and colleagues, you will see some departures from this classical paradigm. If you are serious about conducting your own experiments and you need to be aware about all the possible threats to validity, I think Shedish Cook is your source, because they give more detail and it's more up-to-date, it's more contemporary. And of course, about some special aspects of experimentation like debriefing, you can read it Smith, and in about small n designs also you can find a chapter by Seville and Basket in the handbook by Davis. So in the materials folder, you know where to look. And good luck exploring this literature. At the seminars, we'll play a little bit, spot the confound and identify the independent variables to be able to learn to analyze experiments. But our goal is to train ourselves in spotting those potential confounds, in identifying those potential alternative explanations, because this will allow us to be more critical not only of other people's studies, but also of our own, to design ultimately better studies. And next time, we'll discuss the studies that are not so perfect, but inevitably necessary, correlational and quasi-experimental designs. But that will be after a little while. So see you soon, and thank you for your attention.